So we're continuing our exploration of multi-step syntheses with carboxylic acid derivatives. If you look in 21.27, you'll see a couple things. First, you'll see that the carbonyl oxygen goes away. So we're going to have to replace, and it's not just that it disappears, it's that it gets replaced with bonds to hydrogen. And so that should suggest reduction. If you replace bonds to an electronegative element with bonds to hydrogen, that's reduction. So we're going to use some sort of a reducing agent at some point. The other thing we'll notice is different is that instead of a chlorine, we have an amine. Now, when you look at chlorine on a carboxylic acid derivative, like an acid halide, you'd want to see the chlorine as a leaving group. And if you sort of squint, you can see how the nitrogen could be the nucleophile. So the first thing you could do is you could do a nucleophilic acyl substitution. You can use excess, so more than enough, ammonia, NH3, and that would replace the chlorine with an NH2. Now the reason why you use excess is because when you first add this, you have NH3, which has a positive charge, and a second ammonia can come in and steal one of the hydrogens so that it stabilizes the positive charge. So it does that proton transfer. And so what you'd really want there in the end is NH2. And we've drawn that mechanism in a previous video. So you can do that nucleophilic acyl substitution. And now the only difference is the oxygen. We have these two bonds to oxygen, so we want to replace it with hydrogen. That's a reduction. So we can use a strong reducing agent like lithium aluminum hydride. And then anytime you use that, you just want to follow it up with some water. So overall, the steps for this are first excess ammonia, and then lithium aluminum hydride. And just to even everything out, we'll add some water in there. And that's it. That is the recipe for this one. So it's really just a nucleophilic acyl substitution, the nitrogen for the chlorine, followed by a reduction, replacing the bonds to oxygen with bonds to hydrogen. In 2130, we have an interesting reaction. Here, we have one carboxylic acid derivative, an acid chloride, and we're turning that into a different one, a nitrile. Note that that CN is really triple bonded. The carbon is triple bonded to the nitrogen there. So one thing that we'll notice is when you look at the acid chloride, you see the chlorine as the leaving group. Well, what heteroatom, what atom other than carbon and hydrogen are you replacing that with? You'd be replacing that with this nitrogen. So even if you couldn't get further than that, you could see how you could do a nucleophilic acyl substitution to replace the chlorine with the nitrogen. So if you use excess ammonia, just like we did in the previous exercise, that would make that happen. The first equivalent of ammonia will come in as a nucleophile. You get your tetrahedral intermediate. The oxygen forms the pi bond again, kicks the chlorine off. At first, you would have 3 hydrogens, and the nitrogen would have a full positive charge. Another ammonia molecule would come in and use its lone pair to steal the hydrogen, and so you do a proton transfer to make it NH2. So that is that. So in other words, we've turned the acid chloride into an amide by using excess ammonia. So now, if you look at this again, it's sort of like what we saw before. It's technically not a reduction, because reduction is reducing the number of bonds you have to electronegative elements. Here we have 2 plus 1 is 3, and here again we have 3. So it's not necessarily a reduction, it's just that we want to kick the oxygen off. Notice this oxygen is here, but it is nowhere to be found in our product. Now that oxygen is a terrible leaving group. And to turn it into a better leaving group, to turn an amide into a nitrile, there is only one recipe. And the recipe is thionyl chloride. So that's SOCl2. That looks like this. Oops. Thionyl chloride. that really toxic, nasty stuff. We've seen this before. You can use this to turn a carboxylic acid into an acid chloride, but you can also use it to turn an amide into a nitrile. And so if you're just looking at this from the perspective of synthesis, that's it. That's the end of the story. You have a two-step recipe. But because that transformation probably looks so unfamiliar, I'm going to walk through the mechanism for it. If you're not interested, you can scrub over the mechanism. It's not something that you would have to show me on a test. I want to provide it to you so that you have the opportunity for an understanding, rather than just memorizing this recipe. But you should at least know the recipe. If you have an amide and you treat it with thionyl chloride, you get a nitrile. Okay, how does it do that? Ultimately, this thionyl chloride turns this oxygen into a good leaving group. Okay, so let's draw this. We have, and then you just do a couple proton transfers. So this is going to be really a nucleophilic acyl substitution followed by a couple proton transfers. What's unusual is that the nucleophilic acyl substitution won't be on a carbon. It will actually be on our thionyl chloride, which you could see has a similar structure in it, the double bond to the oxygen. It's kind of like a carbonyl, and so it's susceptible to the same sort of reactions, nucleophilic acyl substitution reactions. Okay, so the first thing that happens is the lone pair on this nitrogen is really in resonance with this pi bond. It's allylic to the pi bond, one atom away from an atom in a double bond. And so it can move over and sort of in a second resonance structure, and you can imagine these pi electrons being somewhat more reactive because of that. And they can act as a nucleophile to attack this sulfur and kicking the pi bond up. So that, if we were sort of thinking about this in terms of the nucleophilic acyl substitution, this would be the nucleophilic attack. So once you have that, you'll have this molecule. This will form a second pi bond, and that pi bond will break. So now we have this. We still have the two lone pairs. Now we have a bond to the sulfur. The sulfur still has two chlorines on it, but it only has a sigma bond to this oxygen, which now has three lone pairs and a full negative charge. So this is sort of like our tetrahedral intermediate, with a very unstable negative oxygen that swoops back down and ends up kicking off the leaving group, which is one of these chlorines. So this, if you were classifying it, would be loss of a leaving group. And you see we've already done the two essential steps in a nucleophilic acyl substitution reaction. We're just doing them on this weird sulfur compound, thionyl chloride. So and this nitrogen, meanwhile, should have a positive charge because it has 4 bonds. All right, so now the sulfur has the double bond to the oxygen and a single bond to just one chlorine, and another chlorine is floating out in space, living its best life. So now all we have to do are a couple proton transfers. The first proton transfer, and you can use any base for this. I'm just going to use water. Well, you would use a base. So I'll use a general base. If you have a base, it can come in and steal one of these hydrogens. So that would stabilize that positive charge, that proton transfer. And now you can almost see where we're going, because we want to form a triple bond between the nitrogen and the carbon, and we want the oxygen to leave. Oops. So we get rid of that hydrogen, that goes onto the base, the lone pair there stabilizes what was the positive charge, and we just need one more proton transfer. If we take another equivalent of whatever base we use, I can steal this hydrogen. The electrons would go toward the carbonyl carbon in this case, and you can see how this whole group leaves as a leaving group. And actually, these electrons end up forming a double bond to that sulfur and kicking the chlorine off as another leaving group. So you sort of have a proton transfer happening here at the bottom, and it's instigating this loss of this leaving group up here. So that ultimately you end up with a triple bond between that carbon and the nitrogen. And I'm drawing that as linear now, but this is the carbon and then the nitrogen. And this leaves as sulfur dioxide. That's a gas. And the other chlorine is off floating around. But you'll notice that overall, in terms of the story of the carbon skeleton, we ended up turning an amide into a nitrile. And the way we did that was really just a nucleophilic acyl substitution. We replaced one of the chlorines in thionyl chloride with the oxygen in the carbonyl, and then we did some proton transfers to get electrons around the nitrogen, and finally this group with the sulfur got kicked off as a leaving group. Okay, so that's the mechanism, but the thing to remember is the way you turn an amide into a nitrile is with thionyl chloride. All right, and then B here, if you look at this one, when you see this, you'll notice a couple things. You have a bromine. Bromine is a leaving group, so you could do a substitution reaction. You have another carbon here. That means you need a carbon nucleophile. Right here you only have one, here you have two. So if you have a new carbon coming in, you have a carbon nucleophile, and you'll notice that that has a functional group on it. Now there are multiple ways you can make this happen, but when you think about forming this new carbon-to-carbon bond, it's a single bond, it's not to benzene, so you're either going to use a cyanide or a Grignard, or potentially a Gilman reagent. How is that? The Grignards have the MgBr, they're strong carbon nucleophiles. The Gilmans have the copper lithium, they're weak carbon nucleophiles. Watch out, the Gilmans will have two R groups. They'll have two there, but you only ever add one. Well, the thing is, all of these will make carbon-to-carbon bonds, but the most efficient one would be the cyanide, because we want the carbon that we add to have a functional group on it, and this has a functional group built into it. Not only that, but this functional group is a carboxylic acid derivative, and we want a carboxylic acid. So we could first do a nucleophilic substitution, do an SN2 reaction, have this cyanide swoop in, attack the carbon, kick the bromine off, and that would give us, and I'm going to draw this as linear because it's a triple bond, so that'll give us that. Here's our one carbon there. Oops. Wait a second, sorry. Drew that incorrectly. So we've got this carbon here, and then the triple bond to the nitrogen. So this is that, and then we have this group attached to it. And then, so now we have our second carbon. So if you compare this to the product has two carbons outside of the benzene. We have two carbons outside of the benzene. We just need to turn the nitrile into a carboxylic acid. And the way that you do that, I mean, we drew the mechanism for this in a previous video on the reactions of nitriles, is to use hydronium. Add H3O+, and it hydrolyzes that. First, it hydrolyzes it to an it hydrolyzes it to an imine, and then it hydrolyzes that. Oh no, I'm sorry. This just goes straight from the nitrile to the carboxylic acid. So that's one recipe. You could use something like sodium cyanide and then follow that up with this acid wash. And that's the most efficient way to make this reaction happen. You could try to do it another way. It's just going to take you a longer time. So if you didn't see that it would be more efficient using the cyanide and you were like, bromine, maybe I can use a Grignard reagent. Well, you can, and there are more and less efficient ways of doing the Grignard reagent. If you were to treat this with just solid magnesium, the magnesium will insert itself in between the carbon and the bromine. So you'd sort of have the magnesium bromide there, which creates an almost ionic bond. So this can act as a nucleophile, and the magnesium would have something close to a positive charge. But if you just want to add one carbon, what type of an electrophile can you use? You might be tempted to have like a substitution reaction, just have a leaving group. You could do that. We'll talk about how you could use that in a second, but you could do it in an even more efficient way if you treated this with carbon dioxide. Then this nucleophile would attack the carbon, open this up, and you would almost have your product immediately. Oops. Sorry. This is supposed to have one other carbon inserted. The principle behind the reaction is the same. I apologize for the mix-up. You'd have the magnesium and the bromine here. All right. So this would then attack this carbon there. So the same idea. You have the one carbon that was there originally, and now this new carbon from the carbon dioxide. It has the double bond to the oxygen, and one now just a single bond there. And so you'd follow that up with acid or just water to protonate it. That would do the proton transfer. So you'd have that there. And that would be your product. So that's another possible recipe. So we saw how you could use a cyanide and make a nitrile and do a hydrolysis reaction. We just saw how you can create a Grignard reagent with magnesium, treat that with carbon dioxide, and then just add a hydrogen on. Now, if you wanted to do an SN2 reaction, you could. It just won't be nearly as efficient. It'll be much longer and more complicated. But just to see how you might think through something like that, you could have this carbon attack this carbon and kick off your leaving group. So standard SN2 reaction. And that would give you ethyl benzene. You can use, this is not very reactive, right? We don't see any leaving groups or functional groups on it. So if you have an alkane like that, you have the benzylic position at your service. You can add NBS and light to put a halogen on there to make it more reactive. And then you can use a base. Now here, there's only one place where you have a hydrogen that the base can steal. There's no hydrogen to the left, so it can only take it to the right. So you can use a base. It could be any base. You can use sodium ethoxide, sodium methoxide, sodium tert-butoxide, and that would do an elimination reaction in the only direction that's open. So that's there. Now, you want an oxygen on that end carbon, so you could do an addition reaction. That would give you this, basically adding an H and an OH. That's anti-Markovnikov because the hydrogen goes on the more substituted carbon. So that would be hydroboration oxidation. And then you just oxidize it with a strong oxidizing agent, like sodium dichromate. and that turns that primary alcohol into a carboxylic acid. The difficult thing with that, and the trouble you might actually run into there, is if you do this, you would actually, you might even saw this off, because the benzoic position still has a hydrogen. So that would be a troublesome mechanism. If you did that, I would give you most of the points, because I'd be very appreciative of how many recipes you'd recognize here. But it's much less efficient, and you'd also run into some trouble in reality, because the strong oxidizing agent would react with the benzoic position there. So the two reactions you'd really want to use, the efficient ones, and the ones that are more relevant for this chapter that we've gone over, are these two up here. Remember that if you add a carbon and you want a functional group on it, making a new carbon-carbon bond with a cyanide is a really good option, because it has a functional group built in. And don't forget, another way to add one carbon, just one, that has a functional group, if you have the opportunity to do a Grignard reagent, is reacting